All right, let's get started then. So last time we talked about how we could change the operating point of a pump within a pipe system through three different ways. We talked about how we could alter the pump speed to shift the pump curve up and to the right by increasing the pump speed, or down and to the left. So that allows us to change the operating point of a pipe system for which we have a variable speed pump. Not all pumps will be variable speed. So we can also achieve changes to the operating point by putting pumps in series or in parallel. So we talked about how we could place pumps in series to increase the pump head. And we talked about how we could place pumps in parallel to increase the effective flow rate of the pump for a given pump head. And we talked about how the pump curve changes when you put pumps in series and in parallel. So we went through a couple of examples. So first, talking about the pump speed, we did an in-class example where we had a pump operating at 2000 RPM. We had the original pump curve for the pump operating at 2000 RPM. We were able to scale the discharge and the pump head by using our affinity laws. So we multiplied the discharge by the ratio of the pump speeds, and we multiplied the pump head by the square of the ratio of the pump speeds. That gave us our new pump curve, shown here in orange. And then we computed the system head curve for this particular system. We could find the new operating point just by finding the intersection between our system head curve and the new pump curve. So we went through an in-class example on changing the pump speed to change the operating point. We also went through an in-class example of how we can use pumps in combination to change our effective pump curve. So we first went through an example of pumps in series. And when you have pumps in series, the resulting pump curve, you can attain it essentially just by adding together the pump heads. So the pumps in series will operate over the same discharge range. You can just take your two pump curves and add them together in the vertical direction, and that will give you the effective pump curve for the two pumps operating in series. So are there any questions on this example with pumps in series? So this one I think was a little bit more clear. Are there any questions on pumps in series? Okay, and then towards the end of class, we started talking about pumps in parallel. And this one, I didn't quite have enough time to explain in detail. But when we have pumps in parallel, we can get the resulting pump curve by effectively adding together the two pumps in the horizontal direction. So adding together the discharges over their shared head range. And we came up with a method for doing that at the end of class yesterday, but I want to redo this portion because I was a bit rushed towards the end of class yesterday, and I want to make sure that this is totally clear. So we want to create a new column in this Excel sheet. So we're trying to add the two pump curves together in the horizontal direction. We need to do that over the shared range of heads. So what was our general approach that we tried at the end of class last time for adding together these two discharges from these two pump curves over the x-axis? What did we need to do first? So first, we have a range of pump heads, and we have the flow rates for a single pump. So these first two columns represent our pump curve, our first pump curve. The first and third column represent our second pump curve. So what was the first thing that we had to do to add together these two pumps in the horizontal direction? What was the first thing we had to do?
Find a cube, one elevation ahead of pump one, or sorry, I don't remember. Identify the cues on the pump curve two that match the heads from pump curve one.
Very good. So that is exactly right. So if we're adding together these points in the horizontal direction, we need to find the discharges that, for the second pump curve, the one in orange, that match the head points corresponding to our first pump curve. So for 300 meters, for example, we need to find the discharge on the orange curve that corresponds to a head of 300 meters. And we need to do that for each of these points on the blue pump curve, our first pump curve. So how did we go about doing that? You'll probably need to know this for the example we're going to be doing in class. Yes?
Had function for the merge curve, and then we use like seek to find the y, the head, the head at that point, like what x that was happening at what flow then.
Very good. So basically, we have a function for this orange curve for our second pump curve that gives us the relationship between the head and the discharge. So we had to we plugged in a value for the pump head corresponding to the pump head that we want. So for the first point, that would be 300. And then we find the value of Q for this polynomial here that gives us a head of 300. So to do that, we can do this using goal seek. Honestly, this isn't the best method for a reason I'll talk about shortly, but it will suffice for now. So we have an initial guess of our discharges. For our objective, we're going to basically try to find the discharge such that this polynomial here evaluates to 300. So we can do that by taking our polynomial, 0.2124 times q squared minus 0.1321 times q, that's cell E2, plus 360.37. And now we're trying to find the q such that this evaluates to a head of 300. So we can do that by subtracting 300 and then finding the q, the discharge, such that this cell evaluates to 0. We can do that using goal seek. Like I mentioned, this isn't the best method for doing this, but it will suffice for now. So we're trying to set cell D2 to value 0 by changing cell E2, which corresponds to the discharge. And if you do that, you should get a discharge of about 16.55. And you can go ahead and do that for each one of these points on our curve. With that, you should have the discharges for the second pump curve corresponding to the heads achieved by the first pump curve. So why is this maybe not the best method for solving these discharges? Some of you might have run into this issue. Yes. Yeah, it can give you the wrong root. There's two valid discharges for this polynomial. So a better approach would be to use a polynomial root finding algorithm and then select the positive root. Unfortunately, Excel does not have a polynomial root solving function. You can do this using Desmos or your graphing calculator or Python and MATLAB if you're comfortable with those programming languages to find these discharges. But essentially, we do this for each one of these here. Instead of putting in 300 hard-coded here, I'm going to reference cell B2. That way I can just drag this whole thing down. And then we can do goal seek for each one. So set D3 to value 0 by changing cell E3. And we just go down the list and do this for each one. And we will end up with the discharges for pump curve 2 corresponding to the heads for pump curve 1. So let's just go ahead and do this all together here. You should end up with numbers like this. If you're not able to get the same numbers as I do, there's a couple of solutions you can do while still using Excel. So one would be to use Solver and then impose a constraint on your solution to make sure that it's positive. So that's one way of doing this without resorting to using an external root finder. The fastest way is probably to use a programming language, but I won't require you to do that. Okay, so we have our discharges for pump curve 2 corresponding to the heads given by pump curve 1. To get the total flow rate through this parallel pump system, we just add Q1 and Q2 together. So this will be Q single plus Q2. And if we do that, we will get our pump curve corresponding to the two pumps operating in parallel. Any questions on this example? No questions. Questions? Okay, so with that, I have two in-class examples. So you started on the pump speed example last time. So for the next 20 to 30 minutes, I'm going to give you a chance to finish up this pump speed example. And I also have another in-class problem. So this problem is using the same pipe system, but now we have two pumps that are operating in series and or in parallel. So we're going to evaluate the operating discharge and the efficiency for the pumps acting in series and in parallel. So let me just give you a quick drawing. So again, this is the same problem that we looked at last time, except now instead of changing the pump speed, we're going to be changing the configuration of the pumps. So again, we have two reservoirs. There's an elevation difference of 10 meters, I believe, between the two reservoirs. And we're going to have a pump here. So you're going to look at the pump operating by itself. You're going to look at the case of pumps operating in series. And then you're also going to look at the case of pumps operating in parallel. So it would be a configuration like this. You have two pipes coming out that join back into your original pipe, each with a pump on it. So for this in-class example, you'll be looking at not only the pump operating point, but also the efficiency under each of these configurations. The efficiency is given by this function here. Eta is equal to negative 11.34 times the discharge squared plus 5.6 times the discharge through each pump. So the efficiency here is a function of the flow rate through each pump. So there is a starter spreadsheet for you to use for this problem. So if you go to lecture 14, go ahead and download pump combinations in class activity blank. So this sheet here will help you get started on this problem. Again, the goal is to find the operating point and the efficiency for the single pump, the pumps in series, and the pumps in parallel, and to compare those operating points and efficiencies. Okay, are there any questions before I let you get started? So I'll give you about 20 to 30 minutes to work on this. We'll reconvene and I will give you some hints, and then we're going to move on to our next subject after that. All right, and there are power strips up here if you need them. Okay, so in the interest of time, I'm going to just reconvene and help you out if you are stuck. So let's open up this problem here. I won't give you the full answers, but if you are stuck, we'll help you out a little bit. All right. So first thing we have to do is probably compute the system head curve. So that's given by the problem statement. So what is our expression for the system head curve? What's our static head requirement? 10 meters plus, and then what is our expression for the head losses? Just give me a number. 55.52 times the flow rate to the 1.85 power. Okay, is that correct? Does that look right? Okay, so we can go and we can plot that. I'm not checking the validity of the answers here, so you're gonna have to tell me if this is wrong. So this is the system head. For the X values, we're gonna want to use this set of discharges that we use to compute the system head curve. And for the Y values, we're gonna want to use our system head. Okay, so that gives us the operating point for the pump acting just by itself. We get about 0.4. Is that right? Okay, so how would we find the efficiency if we know what the discharge is? We can either plug it into the expression that we have for the efficiency, or we can just look at the chart, go over to 0.4 and see that the efficiency is about 0.4256. Okay, so that's the first part. Okay, next we got to compute the equivalent pump curve for the two pumps acting in series. So how do we do that? How do we do that? We have two identical pumps acting in series, right? So we can get the equivalent pump curve for the pump acting in series by multiplying our original HP by 2. It's the same pump. There's just 2 of them. So we can just multiply the original pump head curve by 2. We can multiply the Y values by 2. So let's go ahead and create a new series. So this will be series. For the X values, we're going to use the original Q. For the Y values, we're going to use our pump acting in series. And there we have our pump curve for the pumps acting in series. Okay, now for pumps in parallel, how do we compute the pump curve for the pumps acting in parallel? Is this easy or hard? Hard? There's a shortcut for this particular problem, yes? You can multiply the Q values by 2. So because they're 2 identical pumps and we're adding the pump discharges together in the horizontal direction, all we have to do is just multiply the original discharges by 2. So if you have identical pumps, that makes this easy. So we take our original discharges and multiply them by 2. That will give us our new pump curve. So I'm going to add a new series here for the pumps acting in parallel. For the X values, I'm going to select this set of discharges here. And for the Y values, I'm going to select our original HP. Because remember, we're only multiplying the discharges by 2, not the heads. And you should get something that looks like that. From there, we can just find the operating points through visual inspection, or we can use a numerical procedure to find the intersection. So you'll notice that this system head curve here doesn't go far enough. Is that a problem? How can we fix this problem? Yeah, you could forecast another period. Also remember that the system head curve doesn't depend in any way on the pump curves. So we can just use a different set of cues to compute this system head curve. So what I can do is, let's go back. So let's say we want our system head curve. Instead of using the original set of discharges, let's use this set of discharges over here to give ourselves a bit more range. So instead of A2 here, I can use F2. Okay, we can extend this down. Now, note that this is wrong. I have to go back into the plot, and for our system head curve, I need to select the column F now for our X values. But you'll see that it extends our system head curve further to the right. And from there, we can find the intersection with the pumps acting in parallel. So this is generally what your plot should look like. Again, I have not verified the numbers that you gave me, but I believe this looks right to me. So that's the overall procedure. Are there any questions on this problem? Any other questions? Oh, there is one issue. So you'll note that if you find this operating point here, it'll be above 0.5. If you find the point on the efficiency curve, you'll find that it gives you a negative efficiency. So what mistake did we make here? So first of all, what flow rate should we be using for the pumps acting in parallel if we're trying to compute the efficiency? So, sorry? Right. So when we're looking at the efficiency depends on the flow rate through each individual pump, which will be half of the total flow rate moving through the parallel pump system. So when you're computing the efficiency for the pumps acting in parallel, you need to find the flow rate through each individual pump and determine the individual efficiency of each pump that's being operated. In this case, they'll both operate at the same efficiency because they'll have the same flow rate going through them. Yes.
Values for the extended level.
So just in brief, you can use any set of cues that you want in the system head curve. It doesn't need to depend on the range of cues used for the pump curves. You can create an entirely new column with a new set of discharge values and use that. All right, are there any questions on this example here? Any other questions? So this is due, I think, Tuesday of next week. We should get a little bit of time in class on Tuesday to work on this if you haven't finished. I know that many of you have already finished. So yeah, if you have questions, feel free to bring them up at office hours. With that though, I'm going to move on. And we're going to talk about our last subject for the pumps module. And we're going to tie back pumps with something we talked about earlier. We're going to talk about pumps within pipe networks. So we had previously talked about pipe networks that are operating under the influence of reservoirs. In most cases, real pipe networks will be driven by a combination of reservoirs and pumps. So today we're going to look at how we can actually go about modeling pipe networks that are acting under the influence of pumps. So let's go back to our original example that we looked at for pipe networks. We're going to look at the 3-reservoir system, our branched 3-reservoir system. So we have some reservoir 1, some reservoir 2, some reservoir 3. They are going to converge to a central junction. The junction is going to have an external demand of 1 cubic meter per second. Each reservoir is going to have some water level associated with it, some total head. So for reservoir 1, just using our previous example, this is going to be 250 meters of head. For reservoir 2, we're going to have 150 meters of head. For reservoir 3, we're going to have 150 meters of head again. Just to note, this is QJ. This is the external demand. And then for each pipe, we have some set of pipe parameters. So for the first pipe, we have a length of 2,000 meters and a diameter of 30 centimeters. For the second pipe, we have a length of 1,500 meters, diameter of 0.4 meters. And for the third pipe, we have a length of 2,500 meters. And a diameter of 50 centimeters, so 0.5 meters. Okay, so when we looked at pipe networks previously in this class, what was our general approach for solving the internal flows and heads within the pipe network? What was our general approach? Okay, so there were 2 parts. The first was we apply the continuity equation to each junction. So we applied continuity to each junction. And what else? And we apply energy. And we apply energy to each, I'll say link. But for the cases we looked at, links would correspond to pipes. So we applied continuity at each junction, and we applied the energy equation across each link. Actually, let me write across here instead of 2. All right, so now let's say that we have a pump that is added to this system. So we're going to add a pump right here on link 3. And we're going to be pumping water from the 3rd reservoir to the central junction. So let's just specify some nominal flow directions here. We're going to say that all of the flows are moving towards that central junction. The pump is pumping from this reservoir to this central junction. Okay, so let's go ahead and take this approach, our general approach for solving pipe networks, and let's just start writing down our equations. So we have continuity at junction J. So for continuity at junction J, we have that the flow rate coming from pipe 1, that's Q1, plus the flow rate coming from pipe 2, that's Q2, plus the flow rate coming from pipe 3, that's Q3. That has to equal the flow coming out of the system, which is equal to Qj. So for continuity, we have Q1 plus Q2 plus Q3 minus Qj is equal to 0. Let me write this a little neater here. Okay, next we have to apply energy across link 1. So that's from reservoir 1 to J. So we have H1 is equal to Hj plus the head loss from 1 to J. We have energy from reservoir 2 to J. So in a similar fashion, we have that the head at reservoir 2 is equal to the head at junction J plus the head loss from reservoir 2 to J. And then we have energy from R3 to J. And then previously, when we did this example with just the reservoir, we wrote this as H3 is equal to Hj plus the head loss from 3 to J. For each of these expressions, our head loss, remember, was given by the Hazen-Williams equation in this case. So that is head loss from I to J is equal to 10.7 times the length of the pipe divided by Hazen-Williams coefficient to the 1.85 power divided by the diameter of pipe I to the 4.87 power times the discharge to the 1.85 power in pipe I. Remember that for these pipe network problems, we care about the direction that the flow is going. So what we did was we took the absolute value of the discharge to the 1.85 power and we multiplied by the sign of the discharge to make sure that this head loss was applied in the correct direction. So this is a review of how we solved pipe networks previously in this class. So this was our set of equations for our original branched pipe network example where we only had reservoirs. How would we amend these equations if we wanted to include a pump in pipe 3? What equation would we need to amend here? Energy 3. Okay, so the pump is going to be adding head, is going to be adding energy in pipe 3. What do we need to add to energy equation 3? We need to add the pump head. So to which side do we add the pump head? Left side. So we have that the head at reservoir 3 plus the pump head is equal to the head at junction J plus the head loss from 3 to J. So if we have an expression for the pump head, we can solve this problem using a solver to determine the internal flows and heads within our pipe network system. So basically all we need to do is add our expression for the pump head to our existing energy balances. So what I'm going to do is let's take this branch network example, and we are going to show how we can compute the internal flows and heads if we have a pump in this system. So I'm going to go back to Pages on Canvas. I'm going to go to lecture 9, and I'm going to download our old branch network example. Okay, so this is the completed example for the original branched pipe network. So let's say we have a pump that we're adding to this system. And for the pump, I'm going to use the following pump curve. So this is in Canvas Quizzes in-class branch network with pump. Okay, so we have this system here, and we have a pump curve. So I'm going to take this pump curve and I'm going to go ahead and just paste it into Excel. So this is under Canvas Quizzes. So this is in-class branch network with pump. And I just copied and pasted this pump curve into Excel. So let's go ahead and plot. Insert chart. Let's go with a scatter plot here. There we go. So there's our pump curve. Now, if we want to use this pump curve in our equation, what can we do to make this something that we can put into our energy equation? We have this tabular pump curve here, but we want an expression for the pump head as a function of discharge. Right, we can fit a polynomial to this pump curve. So let's go ahead and do that. So I'm going to go to add trend line. We're going to use an order 2 polynomial, and I'm going to display the equation on the chart. That is very small. But you'll see that this pump curve here can be approximated by this function. HP is equal to -50 times the discharge squared minus 5 times the discharge plus 30. So in general, I'm going to go back to the notes really quick. So when we are adding the energy equation, we'll want an expression for the pump head in terms of some polynomial. So we might have something of the form A times Q squared plus BQ plus C. And we can obtain this by fitting a polynomial or some other function to our pump curve. Okay, so we have a polynomial for our pump curve. Let's go back to our original sheet. I'm going to create a new cell here for our pump head. Okay, and this is going to be equal to, what was our polynomial again? -50. Okay, so it's -50 times, in this case, it'll be Q3 squared. What was the next coefficient? -5 times Q3. And what was our last coefficient?
30.
Plus 30. So we'll have -50 times Q3 squared minus 5 times Q3 plus 30. So this is our pump head. And what we need to do is we take our existing energy equation 3, and all we have to do now is add our pump head to this expression. So we're going to add this new cell for our pump head. Notice that our objective function no longer evaluates close to 0, so we have to run solver again. So I'm going to go to solver. I'm going to set objective E2. I'm going to minimize it by changing variable cells D2 through D5. And if we do, so make a note of these numbers here. Our head is about 118 at junction J. Our flow rate at pipe 3 is about 0.42. Okay, and now I have run the solver. I'm going to run it one more time. All right, and that is our final answer. So what effect did the pump have on our system? What quantities changed here? All four of them changed. But you'll note in particular, the head at the central junction went up. So it went from 118 to 126. And the flow rate in pipe 3 went up from 0.42, I believe it was, to 0.48. Okay, so the pump changed the dynamics of the system. On Tuesday, we're going to do an in-class example using pumps within pipe networks, so you'll get a chance to practice that. We are out of time, so I'll see you at office hours today at 11:30, and have a nice weekend.